In this video, we're going to apply the ideas of angular position, angular velocity, and angular acceleration and talk about rotational kinematics. Specifically, we're going to focus on rotational motion with a constant angular acceleration. We're going to look at descriptions of rotational motion. That's what kinematics is. It's describing the motion of objects. So we're going to look at descriptions of the rotational motion. When we looked at linear motion, we talked about kinematic equations for motion when we had a constant acceleration. We had the equation that related velocity and time. We had the equation that related position and time. And we had an equation that related the velocity to the position of the object. When we have constant angular acceleration, we're going to have very similar equations. In fact, if you make the substitution that x becomes theta, that the linear position x becomes the angular position theta, and that the linear velocity v becomes the angular velocity omega, and that the linear acceleration a becomes the angular acceleration alpha, we have equations that have the exact same form. Instead of v equals v sub 0 plus at, we have omega equals omega 0 plus alpha times t. We have the exact same three kinematic equations, but with rotational variables. And the way that we use these equations is exactly the same as what we would have done for our one-dimensional kinematics, where we list out the quantities, figure out which equation to use, and then go through and solve it. It's the exact same idea, it just has different variables in them relating to the angular positions, angular velocities, and angular accelerations. In fact, we can go further with this, and there are a whole set of rotational equations that we're going to look at, but all of the equations that are listed here are exactly the same form as the linear or translational motion equations. The thing that we have to know is the substitution to make. And so the linear position x becomes the angular position theta. The linear velocity v becomes the angular velocity omega. The linear acceleration a becomes angular acceleration alpha. Mass, which measures the inertia of an object, becomes I, which is the rotational inertia, or sometimes it's called the moment of inertia. Force, which causes acceleration, that's what Newton's second law tells us, becomes torque. Torque causes angular acceleration. And so if we know these five substitutions, all of these translational, all of these linear equations that we have, we can write down the rotational version of them by making these five substitutions. We have the three kinematic equations. Kinetic energy, instead of being 1/2 mv squared, we get 1/2 I omega squared. M gets replaced with I, V gets replaced with omega. So when we talk about energy, we'll see this equation. F equals ma becomes torque equals I alpha. We'll see that equation. That's Newton's second law for rotation. Instantaneous power being force times velocity becomes torque times angular velocity. Momentum being mass times velocity becomes angular momentum L, which equals rotational inertia times angular velocity. These things will all be talked about in later videos, but the form of the equations is exactly the same. So if you know how to solve problems using the translational equations, using the linear equations, it's the exact same process to use the rotational equations. You just need to get used to the new variables. Now I'd like to look at a few examples where we use rotational kinematics to solve. So here we have a wheel, and it has a constant angular acceleration of 4.5 radians per second squared. Again, notice that it says angular acceleration, so it's specifically talking about the angular acceleration alpha. We can also see that from the units, radians per second squared. It's talking about the angular acceleration, not linear acceleration. If it has an initial angular velocity of 1 radian per second, what angle does it turn through in 2 seconds? What is the angular displacement that it has? So the angular velocity, that initial angular velocity, that's omega. Omega is 1 radian per second. Our angle will be in radians. Our angular velocity will be in radians per second. Our angular acceleration will be in radians per second squared. If it's in other forms, if it talks about revolutions, we need to convert that to radians to use in our equations. And so we make a table of our 6 quantities. Initial angular position theta sub 0, final angular position theta, initial angular velocity omega sub 0, final angular velocity omega, angular acceleration alpha, and time. So we let the initial angular position be 0. It has an initial angular velocity of 1 radian per second. It has an angular acceleration of 4.5 radians per second squared. And we want to know what is the angular position, what angle has it turned through from its starting angular position when t equals 2 seconds. And so we use the kinematic equation that relates position and time. But again, it's the one that relates angular position and time. And substituting in, we have that the angular position equals 0 plus omega sub 0 t, 1 radian per second times 2 seconds, plus 1/2 times the angular acceleration, 4.5 radians per second squared, times the time, 2 seconds squared. And so the angle that it has turned through is 2 plus 9, or 11 radians. If you're asked for the angle that it turned through in radians, that would be the answer. Sometimes a question might ask you to go a step farther and give how many rotations has it done. Converting that to revolutions, 1 revolution is 2 pi radians, so 11 radians is 1.751 revolutions, or 1.751 rotations. We often might be asked to switch our answer to revolutions because that is a little bit easier for people to understand. If I say that a wheel has turned 1.5 times, or 2 times, or 4 times, that's easier to understand than saying that the wheel has turned through 6.28 radians, which would be 1 rotation. People have an understanding of revolutions. People don't have as good of an understanding of how much 11 radians is. In the second example, we have a grinding wheel that's initially rotating at 100 revolutions per minute. It's turned off. It has a constant angular acceleration of -2 radians per second squared. We're going to find how much time it takes to stop, how many radians did it rotate through during that time, and how many revolutions did it make while it was stopping. The first step is to convert the revolutions per minute to radians per second. We need our angular velocities to be in radians per second. So 100 revolutions divided by 1 minute, there's 2 pi radians in 1 revolution, and 60 seconds in 1 minute. So 100 revolutions per minute is 10.473 radians per second. And so we set up our table. The initial angular position is 0. The initial angular velocity, omega sub 0, is 10.473 radians per second. The final angular velocity is 0. It's stopping. The angular acceleration is -2 radians per second squared. And we want to know how much time does it take to stop and what angle has it turned through when it has stopped. We use the equation that relates the angular velocity in time. Omega equals omega sub 0 plus alpha t. Angular speed equals initial angular speed plus angular acceleration times time. So 0 equals 10.473 radians per second plus -2 radians per second squared times t. So it took 5.24 seconds to stop. How many radians has it turned through? So we're looking for what is the final angular position after 5.24 seconds, or when it has reached a final angular velocity of 0. So if we use the time, we can relate the angular position and the time. So the angular position equals the starting angular position, 0, plus the initial angular velocity, 10.473 radians per second, times 5.24 seconds, plus 1/2 times the angular acceleration, -2 radians per second squared, times the time, 5.24 seconds squared. Solving that out, we get that it has turned through 27.437 radians. Again, sometimes we're interested in revolutions instead of radians. If someone tells you that something is turned by 27 radians, you might have to think a little bit to understand how much did that wheel turn. Did it turn more than 1 time? Did it turn 5 times, 10 times, 100 times? And so we often convert things to revolutions. Even if we're not asked for this, we often will do this just to kind of understand in our head what was happening. And so converting from radians to revolutions, there's 2 pi radians in 1 revolution. And so 27.43 radians becomes 4.37 revolutions. These problems with constant angular acceleration are very similar to one-dimensional kinematics problems that we would have done at the beginning of the year, as long as you understand these new quantities, as long as you understand angular position and angular velocity and angular acceleration and how to make the substitutions in the equations. In this third example, I want to look at something where we use calculus. So here we're given the angular position as a function of time. The angular position is given by the equation theta of t equals 5 plus 10t plus 2t squared. And we want to find the angular position, the angular speed, and the angular acceleration when t equals 3 seconds. So for the angular position at 3 seconds, we just plug 3 seconds into our angular position equation. It's 5 plus 10 times 3, 10 times t, plus 2 times 3 squared. So we get 53 radians for the angular position. Again, this is like when we had an x of t equation, where we were asked what is the position of the object at a certain time. The angular speed is the derivative of the angular position with respect to time. Omega is d theta dt. So taking the derivative of this, the derivative of 5 is 0. The derivative of 10t is 10. The derivative of 2t squared is 4t. So omega of t is 10 plus 4t. So that would give us the angular speed at any time. If we want it at 3 seconds, we substitute in 3 seconds for t. So we have 10 plus 4 times 3, or 22 radians per second. And then angular acceleration is the derivative of angular velocity with respect to time. It's the second derivative of the angular position with respect to time. So the angular acceleration as a function of time is d omega dt. So the derivative of 10 is 0, and the derivative of 4t is just 4. This has a constant angular acceleration of 4 radians per second squared. It doesn't matter that we're looking at 3 seconds. We could be talking about 0 seconds or 10 seconds or 100 seconds. This is something that has a constant angular acceleration. But if the angular acceleration was not constant, we could find that. We would have had a term here that would have been a t cubed, or a t to the 4th term. If we have position as a function of time, we can take derivatives to get velocity and acceleration. If we have angular position as a function of time, we can take derivatives to get angular velocity and angular acceleration. Or working the other way, if we're given angular acceleration, we can take the integral to get angular velocity, and then we can take the integral again to get angular position. Being able to understand how to go from position to velocity to acceleration, or from acceleration to velocity to position using calculus is an important skill in a calculus-based physics class.